BC dimensions and we will be considering some typical examples. Now, we had introduced in the, we had introduced this particular topic in the last class, but I think that many of the students felt that some more examples and some simplified explanations were necessary, because it's somewhat difficult to grasp the concept of VC dimensions immediately. But anyway, before we present any simplified analysis for that, it suffices to say that the basic purpose of using the VC dimensions is that we would like to evaluate for a particular learning network, okay, for a neural network, be it a single layer or a multi-layer perceptron type, or any other configuration. We would like to know that how many number of patterns we can reliably feed to the system, okay, so that it can accurately classify. Okay. So, for that purpose, VC dimension was providing us with some index. Okay. That is what we were looking for, but we need to understand it in a little more lucid terms, okay, so that it is possible for us to find out the implications of the VC dimensions for any typical learning machine. Now, we are considering fundamentally the learning machines, okay, where the input is going to be in the form of some vector. Okay. Let us say that x vector, that is the input to a learning machine. Supposing this is the block diagram of the learning machine, and we can denote it by a function f, because after all this is the function f, okay, which we are going to realize. In this case, we will be approximating this actual regression function f by the neural network function, okay, f of x w, that is what we had discussed earlier. And this learning machine will be having a set of adjustable parameters. Let us say that we indicate that by alpha vector, okay, which is nothing but the set of, or the vector indicating the adjustment parameters. And we will be getting the output from this network, right. And let us say, for the case of, for the sake of simplicity, we assume that we have only one output, okay, and we indicate the output as y estimated, because this is what we are estimating by using the neural network. Now, our estimation, okay, that may be correct, it may not be correct. In fact, we are for the time being classifying only the binary, the predicted output we are indicating only as a binary thing, so that our y cap or y estimate, okay, that can assume values in the binary domain, that is either +1 or -1, right. And so the thing is that we will be feeding the set of inputs, and we will be adjusting this alpha, okay, such that the classification that we make out of this y is going to be correct, right. Now, what kind of a function can this f be? Okay. We are not putting any constraint into this function f. Okay. What we simply do is that we can assume some different models of this f function, right. So, the first example that we take for the function is that, let us say that we consider the function f, okay, as follows, that this function f naturally, this f will be a function of x vector obviously, and it will also be a function of some b, okay, some constant, okay, or bias which you can think of for the network, and this can be indicated by any typical function, and let us say that we consider a signum function whose argument is x vector dot x vector minus b. Okay. B can be assumed to be a scalar quantity. Now, can you tell me that, okay, I mean let us assume, okay, that x vector is a 2 input vector. So, this is another simplified assumption that we are making, that we will be understanding the VC dimension concept from a very simplified dimensional point of view. So, we are considering a 2 input vector. So, our x vector is a 2 input vector, all right. So, that means to say that the patterns that we are going to have, okay, the patterns will be forming a set of points in the 2 dimensional space. I mean it is easy to imagine or extend the concept to m dimension, because in that case we will be considering that if x vector is an m input vector, then we will be considering an m dimensional space, and there one particular pattern will indicate a point in the m dimensional space. So, here we will be having the we will be having a 2 dimensional vector, 2 dimensional space. Let us say that we indicate this by the x1 and the x2 as the variables in these 2 dimensions, okay. And let us say that this is one particular pattern that we are feeding. So, one particular pattern will be a point in this 2 dimensional space, okay. And likewise there can be several patterns, okay, into it. But if we define the function to be of this form, that it is x vector dot x vector minus b, okay. Can anybody tell me that what is going to be the nature of this function? See, I mean what I mean to say is that here take this argument, okay, take the argument of this signum function. So, what does it mean? That as long as this argument is greater than 0, okay, the input will be classified, I mean whatever input you are feeding as x vector, okay, that will be classified as +1, and if the x vector is such that this argument becomes less than 0, okay, then it will be classified as -1, simply that, okay. So, that means to say that somewhere there will be a decision boundary for this function, okay. And can you tell me that what type of decision boundary does this function realize? X vector dot x vector, it is in the 2 dimension, mind you. I mean just a simple 2 dimensional example. Can anybody like to have a guess? Circle. Yes. I mean anybody feels otherwise? Okay. So, I mean somebody has answered that it is a circle. In fact, it is indeed so, and it is quite easy to verify that. You see, this x vector is consisting of x1 and x2 coordinate and an x2 coordinate. So, it is a 2 element vector, and if you take any particular point, let us say you take this particular point, okay, and then you will be having x vector as this one as the x1 component, this one as x2 component, and if you are taking x vector dot x vector, okay, if you are taking the dot product of that, in that case what are you getting out of it? You are getting x1 square plus x2 square, okay. And what is the boundary equation? That this argument of this equation, that is x dot x minus b, that should be greater than or equal to 0, okay, for a signum function realization, which means to say that x1 square plus x2 square, that should be greater than or equal to b. Now, this is, I mean when you take the limiting case, that is if you take the boundary of the decision, then the boundary of this decision will be x1 plus x2 square is equal to b, and this is nothing but the equation of a circle in the x1 x2 space, all right. So, here the decision function that we are getting is something like this. Let us say that the decision function is realized this way. Of course, my drawing is not indicating a good circle, okay, but I mean this will, I mean once we indicate an equation of this form, okay, if the function assumes an equation of this form, this will definitely form a circle like this. And we will be having different patterns, okay. Let us say that I mean there are two classes of patterns in this, okay. Some classes of patterns are indicated by this color. Let us say that these are the different. So, when I am indicating the patterns with this color, okay, this will indicate an output to be equal to -1, and when I am indicating the patterns with this color, and instead of using the triangle I use a filled circle just to make a distinction between the two categories of patterns, okay. If it is like this, I mean if the set of patterns that we are feeding to the learning machine is like this, where all the I mean all the delta patterns they are -1 and all the filled circles they indicate +1, then you can just see that from the diagram that I have drawn, okay, there is a proper classification that has happened, that all those which are inside, all the patterns which are inside the circles, okay, they will be indicating an output equal to -1, and all the patterns which are outside, they will be indicating +1. Okay. So, this is a decision boundary that we could show out of this. Okay. Now, instead of a function like this, so here the function is of this form, I mean where this is a quadratic function that we are taking. Now, instead of a quadratic function, if we take a simple linear function, then what happens? Let us see that. Let us say that again we take the model as follows, that x is an input, x vector rather is an input, and f is the learning machine for which the adjustable parameters are alpha, and y cap is the output of that. In that case, we can I mean the function f that we are going to realize is as follows, is defined as follows: f as a function of w vector and I mean x vector and w vector, we can indicate as the signum function of x vector dot w vector, where w is also a, I mean here too we assume a two-dimensional space. So, x vector is two dimension, even w vector is also of two dimension. So, in that case what happens is that I mean this is the kind of a function that we take. So, if we take x vector to be x1 x2, okay, and we take the w vector, okay, to be w1 w2. In fact, I mean to write it in a more precise form, we should not write it this way, we should rather say signum of w transpose dot x. Okay. So, that ultimately what we are going to have is w1 x1. So, we will be writing w transpose as a row vector of w1 w2. So, it will be w1 x1 plus w2 x2. Again here the decision boundary will be such that for w1 x1 plus w2 x2 greater than or equal to 0, the patterns will be classified as +1, and for I mean otherwise I mean to say the patterns will be classified as -1. So, here also the decision boundary that we are getting is of the I mean equation of this form, w1 x1 plus w2 x2 is equal to 0. All right. I mean here we assumed that the bias term is 0. Okay. I mean we should not assume the bias to be 0, because typically some bias would be there, okay, even if we assume that B is equal to 0, let us say. Here W1 x1 plus W2 x2 is equal to 0 means that it is a straight line in the two dimensional space, all right, whose slope is going to be what? I mean, it will be minus of W1 by W2, that will be its slope, okay, and intercept in this case is 0 because this is not having any bias. So, the function that we realize out of this is of this form, that we take x1 space, I mean x1 x2 space, and our decision boundary will be a straight line like this, and on one side of it we will be having all the patterns, okay, which are categorized by delta, okay, which will indicate. So, here these deltas will indicate the patterns which give an output equal to -1, and another set of patterns, okay, which will give us an output equal to +1. So, all the filled circles that I am drawing, they will produce an output equal to +1. So, this is the form of the equation. Now, I mean, just to complicate matters little bit, that in the same learning machine we take x vector and we take the function f, alpha the set of adjustable parameters, y cap the estimated output. We take a function f of x vector, w vector and b vector, and we define the function as the signum function of w vector transpose dot x vector plus b. Okay. In fact, this transpose type of representation would have been required here also. So, here also we are taking the x vector definition is a column vector. So, we should indicate this as x transpose x vector. So, that it assumes in the quadratic form. So, you can make this correction that it should be x transpose x vector, I mean in the case of circle, okay. Whereas in this case it is w transpose x vector plus b. So, for this the decision boundary equation will be w1 x1 plus w2 x2 plus b is equal to 0. This is the decision boundary. So, greater than that will classify the patterns into this, less than that will classify into this, and here this b basically is an indicative of the intercept of the straight line. So, if we vary b, then what we are varying is the bias or the intercept of the straight line. So, that is why that whereas with 0 intercept the function f was looking like this passing to the origin, in this case with intercept the function will not pass to the origin, I mean rather that will pass to the origin only in a special case when b is equal to 0, but otherwise I mean with some b it will go like this. So, that the decision boundary will be such that on one side of it we will be having all the patterns that give us output equal to -1, and on the other side we will be having the patterns with output equal to +1. All right. So, these are some of the typical functions that one can take, okay. But I mean we have to really come back to our original purpose of specifying and really understanding that what VC dimension is. Any question at this stage?
So, what are the adjustable parameters alpha? What do you mean by that?
Okay, let's see. I mean this is a good question. The question is that what is this alpha? In fact, I mean here alpha or the adjustable parameters are nothing but w's and b's, that is all. All right. So, typically I mean as a general case I would write that f is a function of x vector and the adjustable parameters alpha vector, where alpha will indicate both b as well as the w's. Okay. Now, in this case I mean I took the simplest of case that we have only 3 adjustable parameters w1, w2 and b. All right. Now, with this type of simplified functional representation in mind, okay, we will give some typical examples of VC dimension. But before we give that, let us define some quantities which we need to define in order to specify the limits of the VC dimensions as indicated by Vapnik, the persons who proposed this VC dimension concept. Now, let us take a quantity of this form. Let us take the expectation of y minus f of x alpha, x vector alpha vector, okay, and we take the mod of this, okay, and as a very typical case I can take it to be half of this, okay. Now, what does this basically indicate? This will, I mean, if I take the expectation of half into mod of y minus f of this, okay, and assuming in this case that y could be assuming a value equal to plus 1 or minus 1, okay. That means to say that if y is equal to plus 1 and f of x alpha is also a plus 1, okay, in that case it is indicating a correct classification, okay, in which case this will be equal to the expectation of this. So, in this case the error will be 0, okay, whereas if we have y as plus 1 and f of x alpha as minus 1, then it will be this mod of this quantity will be 2. So, that is why we are multiplying it by half, okay, so that it will be an error equal to 1. So, for some of the patterns the error will be equal to 0 and for some of the patterns the error will be equal to 1. So, if we take the expectation of this, that is something which is going to lie between 0 and 1. So, we can as well indicate it as a probability of misclassification. So, by this by taking the simplest of assumption as plus 1 minus 1 categorization, we can indicate that this expectation of this quantity is a probability of misclassification for the test patterns. You see here I have purposely indicated this to be y, okay. I did not put any yk, okay. I did not put any training pattern. I assumed that y is a test pattern. So, it is a probability of misclassification, or you can also call it as a test error probability, okay. And this is defined very rightly as E of half of this quantity, and I now indicate this as R test, okay, because this is a test pattern. So, this is R test as a function of alpha, that is equal to E of this, okay. Now, in this case, now let us say that all the training points, so let us assume that all the training points, that is the set of xk, yk, okay, they were drawn as identically independent distribution. So, IID distribution, okay. So, then also the future test points also will be taken from that same IID. Anyway, with that assumption we can define the training accuracy or the fraction of training set misclassified as R of train alpha, which will be equal to 1 upon R into summation half of mod yk minus f xk alpha, okay, mod of this whole quantity where we add it up from k is equal to 1 to R. Now, please take time to understand what I have written. I have assumed that there are R number of, so R is the number of training patterns, okay. I indicate the R to be the number of training patterns. So, there are set of training points x k, y k, where k will vary from 1 to r, and I have indicated the quantity here as summation of half into y k minus this, and what does that indicate? So, overall this when added up, I mean when added up for all the r patterns and then we divide it by 1 by r, that will indicate what? The fraction of training sets which are misclassified in this. Okay. Now, where is the question of training set becoming misclassified? It can obviously happen. You are feeding the training set and you are adjusting the parameters. So, with some adjusted parameters or for some set of parameters, it could be that your network is not classifying the training patterns also properly. So, this R train will indicate that what is the fraction of training set misclassified. So, I should write this as R train alpha is the fraction of training set, fraction of training set Now, without going into any I mean detailed rigorous mathematical analysis, if I ask you that out of these two parameters that we have defined just now, that is R test and R train, okay, out of this which one would you expect to be lower? I mean naturally you would like to have this value of R to be as low as possible, isn't it, because you want correct classification. So, that is why your R should be low. So, out of this R test and R train, which one would you expect to be? Obviously, you would expect R train to be lower, because you are adjusting all the parameters by feeding the training patterns and then only you are applying the test patterns and trying to find out its accuracy. So, naturally, the network is already tuned to the training patterns. So, without going into any mathematical analysis, we can say that R train is going to be less than that of R test, okay, or to
alpha k in this case of R train. You have not used alpha k.
Alpha k.
Xk is a function of xk and alpha k or no, sir?
No, I mean not alpha k. You can say that it is again alpha vector, because what we are doing is that xk yk is a pattern, okay, which is applied on the network, and the network's adjustable parameters are alpha vector. So, I should say xk comma alpha vector.
So, what I need to say is that xk input vector is there, sir.
xk yk is a training pattern, training
For
point.
that it will have some weights w1 or w1 vector we can say.
But but the weights need not be w1 and w2 only. I mean it could be a multidimensional weight, okay. So, whatever free parameters are there in the system, okay. So, I am indicating that all the free parameters in the system, okay, by this alpha vector. So, the free parameters will remain as it is, okay. I mean I am not putting I mean different free parameters for different test patterns. For I mean the free parameter of the systems are adjusted already, I mean you take it that way, or maybe at the end of the pattern. I mean it's not that every independent pattern has got independent this thing. This is a characteristic of the network, whereas xk yk is a pattern. So, let us not confuse between these two. So, now obviously what I mean to say is that our R train is going to be less than this. So, that is why one can express the R test as R train plus something, okay, R test alpha, okay. It is possible to write that R test alpha will be R train alpha, okay, plus something. What is that something? That we do not know, but actually it is Vapnik, okay. He has shown, okay, analytically that with a probability of 1 minus eta. Okay. Eta is in this case, I mean, should not be confused with the learning rate. Okay. Eta in this case is some constant, okay, where it has been shown by Vapnik one very interesting result. Okay. That is what I am presenting to you, because the whole concept of VC dimension actually originated from that. He showed that R test alpha, okay, again I mean I'm not indicating every time alpha to be a vector, I mean I think you please understand that. Okay. R test alpha should be less than or equal to R train alpha plus a quantity which I am writing, it is under root h log of 2r by h plus 1, okay, minus log of eta by 4, this divided by r, where r again is the total number of training points. Okay. Now, in this case eta, as I told, is a constant. So, Vapnik's result shows that with a probability of 1 minus eta, R test can be written like this. Okay. Now, what we do not know is this quantity h, and this quantity h is what is the VC dimension, right. Here h is the VC dimension, but again this result is of no use to us if given a network, given a learning network, we do not know how to measure h. So, we should I mean know that how to get an idea about the h given a network. So, if we know what h is, then naturally h will give us an indication that how to obtain this R test and R train from a given set of training patterns. Okay. Now, in order to arrive at this VC dimension concept, okay, we define what shattering is. In the last class also we defined, but I think that we needed some more examples, without which it is, I mean I can well understand that it will be very difficult to get a concept of shattering. Now, today I am going to define the shattering in a more simplified way. Okay. Now, we can say that a machine F, okay, what is machine F? Machine F is nothing but, I mean these things, I mean the block diagram that we have shown here, this F, the function that we are taking, that itself we are taking it as a learning machine F. We can say that a learning machine F can shatter a set of points x1, x2, etc., up to xr. So, we are taking r number of different training points. Okay. So, it can shatter a set of points if and only if for every possible training set of the form. Now, how are we indicating that training set? Obviously, as x1, y1, okay, x2, y2, okay, up to xr, yr, okay, this many training sets. Okay. There exists some value of alpha. What is that alpha? Again the free parameters. Some value of alpha that gets 0 training error. Now, you see our objective is to have as minimum of training error as possible. I mean, if possible, we will try to have a 0 error. In fact, 0 training error is definitely going to be our objective. Okay, that I mean there should not be any error while at least training the system. Okay. Now, if given r number of patterns like this, okay, it is possible that for some particular value of alpha, okay, the system leads to 0 training error, then we can say that these set of points x1, x2 up to xr, okay, has been shattered by f, okay, shattered, or in other words fully exploited by f. So, let us understand it this way. Now, here you see that once we take x1 to xr, all right, I mean here, okay, now x1 can assume a value of plus, I mean because of the x1 pattern, y1 could assume a value of plus 1 or minus 1. Again for x2 it could be plus 1 or minus 1, okay. So that there will be 2 to the power r such training sets to consider, isn't it? Okay. One of the training sets could be, I mean let us take a example of let us say 4 points, let us say x1, x2, x3 and x4. Okay. So, could be that the training patterns are such that when I give x1 as input, the output is plus 1, when I give x2 as input, the output is plus 1, when I give x3 as input, the output is minus 1, when I give x4 as input, the output is plus 1. If it is like that, then this is a particular training pattern, plus 1, minus 1, minus 1. This is one output that results out of this. Now, there could be, so here with 4 such inputs, we can form 2 to the power 4 or 16 such patterns, isn't it? Okay. I mean the space, the whole space will contain 16 patterns. So, when I have x1, x2 up to xr, then we can have up to 2 to the power r such training sets. Okay. Now, given this example of shattering, I mean given this definition of shattering, that if you can find for a given learning machine, for a given f, if you can find, okay, some adjustable parameters or some values of alpha which will give you a 0 training error, then it is shattered. So, let us now take some very typical example, and again in order to simplify matter, I will take examples from 2 dimensions only, because only 2 dimensions I can represent on a piece of paper. Okay. Although the examples that we will be presenting will be too much oversimplified, but I think that if you understand that, you can extend this concept again to the multi-dimension case. Now, let us take a function of this nature. Let us take that f of x w, okay, to be equal to signum function of w transpose dot x. Okay. If we take it to be like this, then this is the space. Okay. Can you see? Okay. There is some problem with the lighting, so never mind. I mean if you can see, you can continue with that. Now, again we take a 2-dimensional space x1 and x2, all right. Now, if we let us say have only one point, okay. Now, is it guaranteed that it can shatter one point? Obviously, this is the most trivial case, because I can imagine that this straight line passes like this, okay, or a straight line passing like this. So, it is possible to find out a solution, okay, that classifies this point. So, one is actually a trivial case. Now, supposing I take one pattern over here and another pattern over here, Okay. Now, is it possible to shatter these 2 points using a straight line of this form? Are you sure? Answer is yes or no? You are saying yes. Okay. You are assuming, if you assume that this is -1 and this is +1, okay, obviously I can find a solution, a straight line passing like this. But if I take this to be -1, this also to be -1, or I take this to be +1 and this to be -1, I mean both to be +1 or both to be -1, then is it possible to find a solution? It is not. Okay. I mean I can hear some very interesting arguments. Okay. Some people are saying that it is not possible. In fact, that is what is correct, that it is not possible. But again somebody said that we require 2 lines. Okay. It is not that we require 2 lines. Now, I mean let us try to look at it. Again we say that we take the x1 x2 space, all right, and here we take this as a pattern which gives +1 and this as a pattern which gives -1. Now, is it possible to find a line? Okay. It is possible. Only thing is that I mean with both as +1, let us say, with both as +1 or with both as -1, can you separate them? You can. Okay. What you can do is that you have to take a line maybe of this form, this line can. Okay. So, this line's equation will be actually of the form f x b. Okay. Here we have to introduce a bias to this straight line. Okay. X b equal to signum of x x no I mean this will be, yeah, I mean signum of your right, yeah, we should write it as f x w b, okay, as signum of w transpose x, all right, minus b, correct. So, this is the form, and with this type of a straight line it is possible to shatter. Now, let us take the quadratic function, let us take the circular function as we had taken. Okay. Let us consider again x1 x2 space, okay, and we take 2 points, let us say we take 1 point here and 1 point here, and we consider the function f x comma b, which is defined as signum of x transpose x minus b. Now, is it possible for us to define a, I mean shatter this point using this function, shatter 2 points using this function? Okay, see, I mean there you will have to note one thing, that the patterns could be, I mean having any 2 to the power r combination. So, here I have got 2 points, okay. So, my r is equal to 2. So, I can have 4 combinations. I can have this as +1, this as -1, this as +1 both, -1 both, or this as -1, this as +1. So, it is possible for us to define the patterns in. So, I mean I am saying that for all these 2 to the power r combinations, okay, you should be able to find out a solution. Okay, that is it possible to separate out these? it is not possible. You see that I keep on increasing this circle's radius I can increase by using this b. Okay. Now, I can try to set a circle of this. Okay. Again, these 2 points, certainly if I have both to be plus 1 or both to be minus 1, then I cannot separate using these. Okay. So, here you see that the same number of points, that is for just 2 points, the quadratic function is unable to separate. Okay. Whereas, the linear function which we considered just little while back could shatter 2 points. Okay. So, here linear function can shatter 2 points, but a quadratic function cannot. Okay. So, this cannot shatter. Okay. Whereas, in this particular example, this can shatter 2 points.
So, in this you define it as plus 1 plus 1. Now, if you take here also 2 to
Look,
the power r combinations, then again you will not be able to shatter them.
no, for any combination I can shatter. That is the definition. For any of the 2 to the power r, I should be in a position to shatter. You see, I mean here, I mean no matter whether I have plus 1 or minus 1 or plus 1 minus 1 or I mean minus 1 plus 1, okay, I can shatter using this equation. Okay. Whereas, I cannot shatter using a quadratic equation. Okay. Yes.
If both the points are plus 1 and the points lie outside or completely inside the circle,
Both become plus 1 and completely, no, the thing is that you have to consider all these possibilities, that it could be plus 1 minus 1 plus 1, all these four combinations should be possible with these 2 points. Okay. Then is it possible for the circle to shatter? It is not. I mean for a circular function to shatter, it is not. Whereas, given 2 points, okay, any of these 4 combinations, okay, can be shattered by using straight lines, but using circles it is not. Now, let us take the straight line case only, because straight line we can well understand that straight line can shatter 2 points. Okay. Let us increase it to 3 points. All right. Let us say that we have a 2-dimensional space, here x1, x2, and we take okay, 3 points, let us say, okay, plus 1, I mean 3 points. Now, these 3 points could have any combination. I mean there are now how many? 8 combinations possible, isn't it? All of these can be plus 1 plus 1 plus 1. In this case, I take a line like this, it is possible. Now, I take, let us say this as plus 1 and these 2 as minus 1. Okay. I pass a straight line like this, it shatters. Now, I take one of these as I mean 2 of these as minus 1 and this as plus 1, I can have. So, can these 3 points be completely shattered?
In the case if all 3 points are in a straight line and one is plus, one is minus, and then the third is again plus, that is not.
Okay, I mean what is your point of argument? This is a very interesting case that somebody has considered. All the 3 points are collinear. Okay.
The first one is plus 1, second is minus, and the third is again plus.
Plus 1, minus 1 and plus 1. You cannot, yes. This is a typical case where you cannot. Okay. When they are falling in a line, yes. But except for that case, okay, you can shatter, okay, using this. Any?
When you say a function f, does it mean that for every possible combination of x, that is?
No, when I take a function f, I mean I should say that the function f of I mean f x comma w comma b, okay, when it is of the form signum of w transpose x minus b, okay, it can shatter a set of 3 points. That is what I am saying.
No, for different outputs that we are getting now, we found out that okay, we can draw this a line of this form, then a line of this form. That means you are changing the values of b and
Obviously, because my adjustable parameters are w's and b's.
that we can change.
So, what is the definition of shattering? Again, I go back to the example, I mean to the basic definition. You see, machine F can shatter this set of points if and only if for every possible training set of this form there exists some value of alpha. So, that means to say that if I can manipulate my w's and b's such that I can steer it towards a shatter, okay, then it is possible, right. So, up to 3 points we can, all right. Now, let us say that now I increase this and I take 4 points, okay, x1, x2, x3 and x4, 4 points are there in the x1, x2 space, two dimensional space.
In that case, when all the 3 points were lying on a straight line,
Yes.
the shattering it wasn't being shattered. And how do we consider 4 points if 3 points can't be shattered?
Now, this is a particular case. So, that means to say that we have to consider the case of non-collinear patterns, okay, non-collinear patterns.
So then the shattering depends on the actual position, placement of the points. Doesn't depend on any 3 points in the plane can be shattered. We have to specify the position of the points and then we can determine.
Non-collinear, that is all. Once you say non-collinear, so any 3 non-collinear points can be shattered using the function that we had used. All right, I mean using the linear function we could shatter 3 points. Now, using the same linear function, can we shatter 4 points? I think I mean the general consensus that is emerging out of this class is that we cannot. Okay. In fact, you can look at it this way, that you have got 4 points, okay, x1, x2, x3 and x4, and you can have actually here 16 number of combinations of patterns that is possible out of it. Okay. And if you say that you are having I mean x1, x3 to be one class of patterns and x2, x4 to be another class of patterns, in that case you cannot imagine a straight line, okay, that can separate the +1 patterns from the -1 patterns. Okay. In fact, the basic philosophy lies like this, that when there are 4 points, then by joining any 2 pair of points out of these 4, okay, you can have how many? 6 such lines, isn't it? And 2 such lines, they intersect with each other. Okay, the 2 diagonals, I mean if you are taking the line joining x1, x3 and x2, x4, they intersect with each other. So, that is why if you are having I mean patterns which give you +1 values at x1, x3 and which give you -1 values at x2, x4, okay, then it is not possible for you to pass any straight line. Okay. However, adjustment you can do with w's and b's, okay, it will not be possible for you to have that. So, naturally 4 is ruled out. So, how many points could we shatter using the linear function? We could have 3, okay, 3 non-collinear points. So, in this case I should say that H is equal to 3. Okay. So, the VC dimension for this particular, I mean for a special case of 2 dimensional case, okay, when we have only x1 and x2 as the variable, there H becomes equal to 3. That means to say that up to 3 patterns we could shatter, okay, or out of 2 to the power 8 combinations, 2 to the power 8 combination, I mean 2 to the power 3, that is 8 combinations could be shattered, or rather 3 points could be shattered. Okay. So, the VC dimension H is equal to 3. So, when the dimension, that is m is equal to 2, we have h is equal to 3. Now, it is possible to extend this analysis for higher dimension. When m is equal to 3, then we can show that h is equal to 4, and when m is equal to 4, h is equal to 5. So, the law that emerges is that h is equal to m plus 1, okay, 1 more than what the dimension of the system is. So, that means to say that if we are taking, let us say, a 5 dimensional input x1, x2, x3, x4, x5, okay, that means to say that up to 6 patterns can always be reliably separated, or reliably separated means the correct classification exists up to 6 patterns. But this result is somewhat worrying to us, because if we are spending our time and energy to build a 5 input network and ultimately we show that it can only classify 6 patterns, okay, we are expecting somewhat more than that, isn't it? So, that is why, I mean, we have to see that whether a single layer network is good enough, or if we go in for a higher layered network where we cascade I mean one layer with another, then whether we can increase the VC dimension or not, that is something what we have to see later on. All right. So, that is all for today's class. So, in the next class we will be discussing 1 or 2 more points related to this VC dimension, and then we will go over to the next topic, that is the single layer perceptron. Thank you very much.